Topic 128 Introduction to Z Language. So basically, the Z notation is a language and a style for expressing formal specifications of computing systems. यानी हम Z जो है ये एक नोटेशनल लैंग्वेज है जिसे हम फॉर्मल स्पेसिफिकेशन जो किसी भी कंप्यूटिंग सिस्टम्स की होती हैं उन्हें एक्सप्रेस करने के लिए यूज करते हैं. It is based on a type set theory and the notion of a schema is one of its key features. Basically, set theory has both rules and axioms. While type theories only have rules, set theories are built on top of logic. So an axiom is a logical statement accepted as true without a logical derivation. Schema consists of a collection of named objects with a relationship specified by some axioms, and Z provides notations for defining schemas and later combining them in various ways so that large specifications can be built up in stages. Schemas can have generic parameters, and there are operations in Z for creating instances of generic schemas. So before going on schemas, if we see the problems of producing reliable software quickly and economically have been widely discussed in recent years. And initial experience has indicated that the use of mathematical modes of specifying and designing software can contribute towards a solution. So for these mathematical methods to become effective in industrial practice, certain prerequisites must be satisfied. First, the notations used to express specifications and designs must be standardized so that workers on large projects can collaborate without misunderstanding. The second, software tools will be needed to assist with the storage and organization of specifications and designs and to automate the manipulation of mathematical text. Both these prerequisites demand that the mathematical notation be stable and well understood. So the style of software specification and design known as Z has had a long period of development which has for the most part been characterized not by stability of notation but by its very opposite. The Z style has developed as a result of tackling practical examples and adapting the notation to their needs, and this has resulted in a style and a notation which are suitable for the specification of sizable software systems. As the method has become mature, the need for radical changes in style and notation has seen development of Z is now at a stage when a standard notation can be fixed. As I said, this will help to satisfy the need of industry as well as the need of further research into specification processing tools. Now let's move on use of schemas. As I said before going on schemas, as I discussed with you about the problems of producing reliable software quickly and economically have been widely discussed in recent years. So the use of schemas allows the specification to be presented gradually with a close correspondence between the mathematical text and prose commentary. This makes it easy to explain the mathematics as it is presented and to relate the variables in the mathematical text to the system they describe. Okay, let's move on an example. The example is a small database recording people's names and their telephone numbers. Okay, The operation of the database with correct input will be described first, then the schema calculus will be used to extend the specification to deal with errors in the input. Okay. The example is the database contains a number of people names, and against each name is stored a telephone number. It has operations for adding a new name and telephone number, and for inquiring what number is stored against a given name. The state space of the database system is described by a schema called PhoneDB. यानी ये एक phone की database है. Two observations of the state are introduced as components of the schema as the set known of names known to be database. Okay, this one, and the partial function phone, this one, which records a telephone number against certain names. Okay, an invariant relationship between these observations is documented, that the names known to the database are exactly those for which a number is recorded. Let's move on next slide. What are the possible state of the system? So as we discussed the phone database, the possible state of the system is, as an example, the following is a possible state of the system. This one. Even simple mathematics like this allows a degree of exactness in specification which is not easy to achieve with ordinary prose. So as we have specified precisely that each person can only have one number, and that two people may share a number as Jones and Robinson do in the example stage. We can see here that Jones and Robinson have the same number. We have also avoided undesirable implications in specifying the state space. There is no implied limit on the number of entries, nor is there an implied order in which they are stored. It has also been possible to describe the state space without making a premature decision about the format of names and numbers. Topic 129. Why formal semantics? A guiding principle of the Z approach to specification has been the use of the ordinary structures of mathematics in the writing of software specifications. There are several advantages in this. The familiar language of sets and relations proves to be sufficient to describe succinctly means, let's suppose we can say it in Urdu, mukhtasir taur par, or in shortly, the abstract structures needed in programming, and is already known to every mathematician and also to many non-specialists. In following ordinary mathematical practice, we may notice that mathematicians, at least those who call themselves applied mathematicians, spend little time worrying about the formal semantics of the notations they use and the rules of inference used to manipulate them. So why formal semantics? Why should we be concerned with these things when trying to apply mathematics to the new sphere of software design? The first one is, a first answer lies on the nature of the notations themselves. The ordinary mathematician can regard his notation mainly as a system of abbreviations, so that the parts of a text written in mathematical notations are not different in kind from the parts written in English, at least as far as content is concerned. Of course, the form of mathematical notation suits it for purposes for which plain English text would be highly unsuited. The compactness and regularity of formula make them easy to manipulate algebraically in way that English text is not. But in their content, mathematical formulae can finally be regarded as abbreviations for admittedly very lengthy English sentences, and by carefully introducing his notations one by one, the mathematician can maintain his confidence that they are free from ambiguity. Connected with this character of mathematical notation as a system of abbreviation is the way in which the constant symbols in a formula refer to abstract mathematical objects almost in the same way that proper names refer to people, streets, and cities. So when we begin to construct mathematical description of software, it soon becomes plain that one of the main difficulties lies in the sheet size of the descriptions which result. For this reason, it becomes necessary to introduce explicit means for giving structure to the description by naming parts of it and referring to these named parts from other parts of the description where they may be combined and extended in various ways. So the second argument in favor of formal semantics is its consequences for the practice of specification. A formal semantics provides a foundation for a logical calculus for reasoning about specifications and deriving consequences from them. Deriving consequences from a specification is an important aid in checking that a specification captures correctly a customer's requirements and in validating proposed implementation. So formal semantics also provides a view of specifications which abstracts from inessential details of syntax and presentation, and this view makes it possible to compare specification techniques in an objective way and to investigate new specification language constructs. I hope so you understand these two arguments. The first one lies on the nature of the notations themselves, and the second in favor of formal semantics is its consequences for the practice of specification. Topic 130, Meta-circularity. The formal semantics of the Z notation given in this book is itself written using Z as a meta-language. So basically a meta-language is a form of language or set of terms used for description or analysis of another language. Okay, I hope you understand the meta-language. This idea of using a notation to give a meta-circular description of its own semantics forms a long-standing tradition in computer science. In informal terms, if someone didn't understand Z at all, we could hardly expect his understanding to be improved by a look at a formal semantics written in Z. Although, perhaps if he had a partial understanding, he could use the semantics to clear up some remaining areas of doubt. More formally, we might hope that the desired semantics might be found as a fixed point of the definition. So as an example, a more subtle problem is that two slightly different but inconsistent suppositions about the semantics can both be supported by a meta-circular definition. For example, unless special precautions are taken, a meta-circular definition of a programming language will not tell us whether parameters to subroutines are passed by name or value. If we read the text of the definition under the assumption that parameters are passed by name, then the definition will appear to describe call by name, and if we assume call by value semantics, then the definition will appear to describe call by value compare. So why do these criticisms not invalidate a meta-circular definition of Z? Basically, semantics consists simply of the development of certain mathematical theory, and this development could at least in principle be carried out without using Z, but rather say the basic language of first order logic. So this argument encourages us to see the meta-circular semantics ultimately as an informal sketch of a semantic which might be formalized fully in some more primitive but less expressive logical language.